China's Tiangong space station is not just China's version of the ISS. It is a compact second-generation orbital lab that shows what you can do when you build a station after 3 decades of hard lessons. Instead of trying to rival the International Space Station in sheer size, China built something smaller, denser, and more modern. A T-shaped machine engineered around tight mass budgets, careful power management, and the daily realities of keeping a small crew alive and productive roughly 400 kilometers above Earth. To see what the news rarely explains, you have to follow the hardware. How much space is actually pressurized, where the power comes from, how experiments are handled, and how people move through this metal habitat that circles the planet every 90 minutes. The basic numbers already tell a different story from the headlines. In its current configuration, Tiangong masses around 100 metric tons and stretches about 55-56 meters end-to-end, with a total pressurized volume of about 300 per 40 cubic meters, of which only 122 cubic meters are classified as habitable living space. Wikipedia. By contrast, the ISS has roughly 900 to 1,000 cubic meters of pressurized volume, and about 388 cubic meters of habitable space for a similar maximum crew of 6. NASA. So Tiangong is roughly 1/3 the volume of the ISS, and about 1/4 its mass, but is built with far newer electronics, life support hardware, and robotics. Instead of a sprawling orbital city, it's closer to a well-equipped research vessel. At the center of Tiangong's T-shape sits the Tianhe core module, launched in April 2021. Tianhe is about 16.6 meters long, 4.2 meters in diameter, and has just over 100 cubic meters of pressurized volume inside a roughly 22-ton airframe. EO portal. It houses the main computers, guidance and navigation systems, life support, and the propulsion used to keep the station from gradually falling out of orbit. The forward end of Tianhe features a multi-port node where Shenzhou crew vehicles, Tianzhou cargo ships, and the future Xuntian space telescope can dock. At the aft port, a Tianzhou freighter periodically attaches to deliver supplies, remove trash, and perform reboost burns that keep the station in its 380-400 kilometer orbit. Extending from either side of Tianhe are the 2 laboratory modules, Xuntian and Mengtian. Each is close to 18 meters long and around 4.2 meters across, with launch masses in the low 20-ton range. NASA's spaceflight.com. Xuntian is focused on life sciences and human research. It carries racks for biology experiments, environmental monitoring equipment, and extra sleeping quarters used during crew handovers when 6 taikonauts are briefly on board. Mengtian is optimized for microgravity physics, combustion, and materials science. One of its key features is a dedicated cargo airlock that can move experiment packages from the shirt sleeve interior into the vacuum of space and back again without needing a crew member to go outside during every payload swap. Tiangong's exterior is designed as usable real estate, not just structure. Standardized mounting points and planned cable paths turn the whole of Xuntian and Mengtian into long experimental verandas. Design documents and public briefings describe a station that can host more than 24 standardized internal experiment racks and several dozen external payload adapters on the lab modules and future telescope interface ports. China Space Report. These sites support experiments in fluid physics, cold atom behavior, combustion without buoyancy, materials exposed to radiation and vacuum, and long-duration biology. The glamorous launch is the noisy part. The real mission is years of quiet, carefully logged data flowing through those racks and mounts. Robotics are what make that external space practical rather than decorative. Tiangong carries a 10-meter main robotic arm that can grip fixtures, move large equipment, manipulate external payloads, and even help reposition modules. Xuntian adds a smaller, roughly 5-meter arm that can crawl around the station by grabbing successive base points. Linked together, the 2 arms can act as a 15-meter system with reach comparable to the ISS's Canadarm2, but designed in one coherent hardware generation instead of accreted over many years. Every meter of robotic reach saves oxygen, risk, and crew time that would otherwise be spent on spacewalks. And it turns the station into a construction and servicing node rather than a frozen, unchangeable sculpture. Inside, Tiangong looks very different from the famously cluttered ISS imagery. The internal diameter of Tianhe, Wentian, and Mengtian is similar to many ISS modules, around 4.2 meters. But the Chinese modules are longer, which means fewer junction nodes and more uninterrupted cylinder. Instead of a dense web of exposed cables, laptops, and velcroed bags running along every surface, most of Tiangong's walls are covered in smooth white panels. Instruments and racks can be folded away and hidden when not in use. Many subsystems communicate over internal networks and wireless links, reducing the need to snake big cable bundles through narrow passages. It makes for cleaner video clips, yes, but more importantly, it simplifies labeling, reduces snag hazards, and keeps emergency pathways easier to clear. Human factors show up in 1,000 small decisions. Tiangong's modules are lined with foot restraints and handholds that encourage crews to adopt a shared sense of floor and ceiling. In group photos, taikonauts are usually upright, feet anchored to one wall instead of hanging at random angles. That might look like mere formality, but it makes it much easier to run checklists. Look up to the right, grab the valve near the floor, without confusion. The station's lighting system can shift from bright, cool work light to warmer, evening-style tones, and then to a dimmed night mode, to help crew circadian rhythms cooperate with a world where the sun rises and sets 16 times a day. The daily schedule mirrors that same pragmatism. Tiangong operates on Beijing time. Crews typically wake around 7 a.m., check in with mission control, and start formal operations around 8, even as the station crosses the day-night boundary every 45 minutes. In early afternoon around 13:30, the plan calls for a 1-hour nap. To outsiders, this can look like a cultural quirk. To flight surgeons, it is an extra layer of life support. Chronically sleep-deprived astronauts make subtle navigation and system errors that no amount of redundant hardware can fully guard against. Inside a small cabin, a taikonaut might still feel the familiar guilt of resting while others work. But the station's procedures are designed to treat that impulse as noise, not as heroism. Food is where engineering, culture, and morale collide in a surprisingly technical way. Tiangong carries on the order of 120 different food items, with menus customized to each taikonaut's preferences within strict nutritional constraints. Traditional Chinese dishes, spicy chicken, black pepper beef, pickled vegetables, are there not as a nationalistic flourish, but as sensory anchors in an otherwise alien environment. A refrigerator keeps fresh fruit and vegetables usable between Tianzhou cargo runs, and a small greenhouse supports experiments with growing lettuce and cherry tomatoes in microgravity. Every successful harvest and every logged data point from those plants feeds directly into planning for future missions far from Earth, where frequent resupply is impossible. The most talked about galley hardware, though, is Tiangong's space microwave, a compact oven that can heat meals for 3 crew members in about 7 minutes without overloading the station's electrical system. It reportedly took close to a decade of development to build a design that could survive launch vibrations, operate safely in microgravity, and fit into tight power and thermal budgets. The ISS still relies mostly on food warmers and water rehydration systems that can take 20 minutes or more per meal cycle. The difference sounds minor on paper, but over months in orbit, shaving that much time and friction from every meal changes how much crew attention is available for actual research, instead of waiting for dinner to be ready. Exercise hardware is less photogenic, but absolutely central to Tiangong's concept. Microgravity quickly weakens muscles and strips calcium from bones, so taikonauts spend around 2 hours per day on structured workouts. Wentian hosts a cycling machine that drives both upper and lower body, while other stations in the complex hold rowing and resistance systems that mimic the loading patterns of squats and deadlifts without using free weights. Experimental elastic gravity suits thread light resistance into clothing itself, gently pulling on joints and muscles whenever the wearer moves. The idea is to spread physical training across the whole day, instead of compressing it into a single miserable session that is easy to cut when schedules get tight. All of this human-centered infrastructure exists to support Tiangong's real product, scientific and technological data. Across Tianhe, Xuntian, and Mengtian, internal racks and external mounts host experiments in fluid physics, cold atoms, combustion, materials, biology, and Earth observation. Short-term payloads arrive on Tiangong cargo ships and return to Earth in re-entry capsules. Longer-term packages sit bolted to the outside, soaking up radiation and vacuum for years. Mengtian's cargo airlock, combined with the paired robotic arms, turns many payload changes into routine operations, rather than high-risk events that demand multiple spacewalks. The next big step in this architecture is the Xuntian Space Telescope. Public plans describe a 2-meter primary mirror and a camera with about 2.5 gigapixels, yielding a field of view hundreds of times larger than Hubble's, while maintaining similar resolution in its central area. Wikipedia. Xuntian will normally fly free in a nearby orbit, but it is designed to rendezvous and dock with Tiangong periodically for maintenance, upgrades, and refueling. That is a different philosophy from most post-Hubble telescopes, which are treated as largely unserviceable after launch. In this model, the station is a maintenance hub for a small fleet of specialized spacecraft, not just a destination in itself. None of this hardware floats in a political vacuum. The reason there are 2 separate major space stations in low Earth orbit is not because physics demands it, but because law and strategy did. U.S. legislation has long restricted NASA from direct cooperation with China's human spaceflight program, and the IS partnership was essentially full by the time China reached the point of building a permanent station. Rather than accept permanent exclusion, China built Tiangong. From the launch of Tianhe in April 2021 to the relocation of Mengtian into its final port in early November 2022, basic construction took about a year and a half, a rapid build by historical standards. Wikipedia, ISS assembly, by contrast, stretched over more than a decade of shuttle flights and international launches. As the ISS ages and partner agencies talk openly about deorbiting it, sometime in the early to mid-2030s, Tiangong is positioning itself as one of the successor platforms. Chinese officials have already announced training for Pakistani astronauts and have discussed flying crews from other countries that never had realistic access to ISS seats. Time. For emerging space nations, a few seats to Tiangong may offer a cheaper, quicker path to orbital experience than building a domestic station from scratch. Those invitations, in turn, become diplomatic tools, a way to reward cooperation, advertise technological strength, and shape the narrative of who belongs in orbit. There are trade-offs baked into this choice of a smaller, nationally controlled station. One country can make decisions faster, maintain focus across political cycles more easily, and move hardware from drawing board to orbit without navigating a half-dozen parliaments. But risk is concentrated too. Debris strikes, launch failures, or budget crises land overwhelmingly on one agency and one government. Engineers mitigate what they can with redundant life support, shielding against micrometeoroids and orbital junk, and fallback modes that allow modules like Xuntian to assume some control functions if Tianhe fails. Still, the strategic wager remains that the scientific, industrial, and diplomatic returns from operating Tiangong for a decade or more outweigh the vulnerabilities. Seen side by side, the ISS and Tiangong look less like rivals in a sports league and more like 2 points along a learning curve. The ISS, with about 4 times Tiangong's pressurized volume, and roughly 75-90 kilowatts of electrical power from its solar arrays, up to around 120 kilowatts as newer arrays come online. NASA is a sprawling construction project that could only exist in a narrow historical window of shuttle launches and post-Cold War politics. Tiangong, with roughly 1/3 the volume and about 1/4 the mass, is closer to a modern research ship. Compact, purpose-built, and optimized for a steady cadence of medium-length missions and experiments. Both are engineering achievements. Both are fragile. Both are prototypes for whatever permanent infrastructure humanity eventually decides to build in orbit. The most important thing the news usually misses is that none of these machines are magic. They are stacks of aluminum and composite panels, pumps, pipes, batteries, computers, valves, and code, held together by relentless checklists and boring repetition. Tiangong's clean white walls, its foot loops and elastic workout suits, its personalized menus, nap schedule, crawling robot arms, and future serviceable telescope are not decorations. They are specific answers to specific constraints. Limited mass, limited power, limited crew time, and the very human tendency to make mistakes when tired, lonely, or overloaded. Once you understand that, it becomes much harder to treat any station, Chinese, American, or otherwise, as a simple scoreboard about who is winning space. Learning to look past the flags and ask how much volume, how much power, how many experiments, how much crew time does this hardware really support? Turn stories about Tiangong into useful information rather than distant curiosities. Those numbers tell you how ready we truly are to build bigger habitats, fuel depots, or industrial platforms in orbit, and what trade-offs are already being made that will echo in the designs of tomorrow's vehicles. In that light, China's heavenly palace is more than a symbol of national ambition. It is another hard-won lesson in how to keep a handful of people alive and working in a very small metal world, circling endlessly above the much larger one we all share. https n.wikipedia.org wiki Tiangong Space Station UTM source ChatGPT.com Tiangong Space Station now on https now www.nasa.gov international Space Station facts and figures UTM source ChatGPT, International Space Station, facts and figures. https://www.eoportal.org satellite. Missions Tiangong Space Station, UTM source ChatGPT, Tiangong Space Station. https://www.nasaspaceflight.com 2022. 10 China launch. Mengtian UTM source and ChatGPT, China launches Mengtian science model to Tiangong. And https://ChinaSpaceReport.wordpress.com spacecraft Tiangong UTM source ChatGPT Tiangong to China Space Report WordPress.com https://time.com 621 China Tiangong Space Station role as categories TM source ChatGPT China's Tiangong Space Station has a big role to play